Okay, the first thing I wanted to do for this lecture is move on to the page that's marked directly proportional versus inversely proportional. That would be this one, only don't get the answers. And we can go over some of this now. It's looking at some equations and deciding whether things are inversely or directly proportional. And I don't know what it is about that word. That's like the third time today I've run out of space to write it. But anyway, it starts with number 6. If I ever have an excess of free time, my goal is to sort of go into this math handout and edit it. I don't know where 1 through 5 went. But anyway, number 6 is consider the equation P equals Ft. Again, this is impulse equals force times time. It's an equation we saw a little bit a while ago. And if time is held constant, then impulse is proportional to force. Okay. And so the question is, first of all, is P inversely or directly proportional to F? Well, since there's no ratio involved on either side, that's another way of saying that they are directly proportional to each other. So directly would be our answer here. And as F increases, what happens to P? Well, directly proportional means the same thing happens to both quantities. So it increases, and not only does it increases by the same factor. Okay? So number 7, we have the equation power is work over time, which is an equation that we saw before also. So this is a bit of a review. So anyway, if W is held constant, then the relationship between power and time is inverse. Power would be proportional to 1 over time. And of course, that's an inverse proportion. And if time increases with, that is with work held constant, then power decreases because it's taking you longer to achieve the same amount of work. All right, well, the next page has graphs of inverse and direct proportions. We don't really need to go into this in detail, but just notice that the page that shows speed versus time, that's a direct proportion, and it graphs out a couple for an object dropped on Earth versus an object dropped on the moon. Speed changes linearly with time when you drop something. Okay, so speed is directly proportional to time. And here are the data for the Earth and the data for the moon. Things drop faster on Earth because gravity is greater on Earth. But either way, it's a direct relationship. And also, we have an inverse relationship. pressure versus volume for a gas. As long as temperature is held constant, and I will, in fact, go as far as writing that in. As long as temperature and the number of gas particles would be held constant, then pressure and volume are inversely proportional. You can kind of think of that as like squeezing a balloon, or taking an empty Coke bottle, plastic, Coke bottle that's empty, putting the cap on it tightly so it's airtight, and try squeezing it. And as you squeeze it, the volume goes down. As you squeeze it, you're putting more pressure on it, and therefore the gas particles move closer together. Remember that, actually, we haven't really gone over that yet, but they're able to do that because the particles in a gas are far apart from each other. There's a lot of empty space between them. So it's easy to push gas particles together. And so up to a limit anyway, the volume is inversely proportional to the pressure. So if you double the pressure, you cut the volume in half. If you cut the pressure in half, you double the volume. And that's what this graph here is showing. That's what an inverse proportion looks like. Okay, so we're not going to do a lot with graphing. I just wanted to show those so you get the idea of it. The next thing is that we're going to spend a little time with density. Density, actually, as it turns out, is what's known as an intensive property. And what that means is it doesn't matter how much of the stuff you have. So the density of lead is the same regardless of whether you've got a little bit of lead or a lot of lead. Lead is lead, and it has the same density no matter how much you have. Density is mass of an object or sample relative to its volume. And the equation would be D equals M over V, mass over volume. Interestingly enough, mass and volume are both what's known as extensive properties. And what that means is that they do depend on how much stuff you've got. Obviously, the more stuff you've got, the more mass you have. And the more stuff you've got, the more volume you have. But the interesting thing is when you take one extensive property and divide it by another, you get an intensive property, which doesn't depend on how much you've got. Another interesting thing about density is that it is a characteristic property of any given substance. When we say substance, though, in chemistry, we usually assume that we're talking about a pure substance. So the substance would need to be pure. But the point is, what we mean by characteristic property is that the density always goes with that substance. It's sort of a density is uniquely associated with that substance, and vice versa. So water has its own particular density. And as long as it's pure water, it will always have that density as at a given temperature anyway, no matter where that water came from. And so you could say that a given substance always has the same density. That's regardless of where you get it from. As long as, say, if it's pure water, then it doesn't matter whether it's pure rainwater or pure distilled water that you bought in the grocery store or what, as long as it's pure water, it will always have that particular density. Copper will always have a particular density, and it doesn't matter whether it's a copper pipe or where else would you get pure copper? Any other kind of pure copper you might have picked up off the ground, because copper is unreactive enough that sometimes you do find it in nature as copper metal. So, if it's copper, then it has the density of copper. And what that means is that density can be used to identify a substance. Since each given substance always has the same density, that means that scientists have had plenty of time to study the densities of various substances and to record them and to measure them really accurately. So, for any given substance, you can probably look up its density. So the fact is that we often use densities to identify a substance. If you've got, say, a piece of gray metal and you're not sure what it is, because all metals are some shade of gray except for gold and copper, which are gold and copper colored, of course. You've got a piece of gray metal and you're not sure what it is. Well, one way you can identify it is by finding its density and compare that density that you found to the known densities of the various metals. And you could probably at least narrow it down, if not uniquely identify the metal just by having its density. Okay, the equation and so actually we already had the equation, but I'll write it once more. And remember that in physics, we also have the symbol rho. So you might see that, for instance, in the book. The variables in the equation, well, we've got density, or rho, or density, and that normally has the units of grams per cubic centimeter. But actually, it could have any units of mass over units of volume. So grams per cubic centimeter are kind of the standard units that we use in chemistry and physics, but they could vary. As long as you've got a mass unit over a volume unit, it's a density of some sort. And M is mass, and that's usually measured in grams, and V is volume, which is usually measured in cubic centimeters. Whoops. And so the characteristics units that we use for density actually varies with the state of matter. So for solids, we usually give the units of density in grams per cubic centimeter. But for liquids, it's usually grams per milliliter. But if you remember back to when we were talking about the metric system, I mentioned that milliliters and cubic centimeters are actually the same thing. So grams per cubic centimeter and grams per milliliter are actually the same thing. It's just a different way of expressing it. Solids, we tend to report it in units of grams per cubic centimeter because we're assuming that the solid is a regularly shaped solid, so that we can measure its volume as some sort of length times width times height sort of situation. And length and width and height would all be measured in centimeters, so the volume technically would be cubic centimeters. For liquids, we usually give the units as grams per milliliter because we'll usually be measuring the volume of the liquid in a graduated cylinder, which is, like it's like a fancy measuring cup that we use in the laboratory. And it's marked off much more accurately than measuring cups are, though. And the unit on most laboratory glassware would be milliliters for volume. But actually, sometimes if you have an irregularly shaped solid, we'll measure the volume by displacement of water. That is, you put some water into a graduated cylinder, you carefully drop the solid object into the graduated cylinder, and you see how much the volume of water goes up. And the amount by which the volume of the water goes up should be the same as the volume of the solid. And in that case, you're actually measuring the volume of the solid directly in milliliters. So they're kind of interchangeable. For gases, we usually use the unit grams per liter because gases are very diffuse, which is kind of the opposite of dense. The particles in gases are very far apart, and so we measure the mass in grams, but we use a larger volume for the unit, just so that we'll have a convenient number of grams within that volume to deal with. Gases are so diffuse that if you reported the mass or the density of gases in grams per milliliter at room temperature and normal atmospheric pressure, most gases would probably come out to be somewhere in the neighborhood of maybe 0.002 grams per milliliter, while grams per liter would be more like 2, which is a much more convenient number to deal with. So grams per liter is what we usually use for gases. Okay. If you look up densities of various substances, you'll find that, for instance, the density of aluminum is 2.70 grams per cubic centimeter. Okay, so that means that each cubic centimeter of aluminum has a mass of 2.70 grams. If you have 2 cubic centimeters of aluminum, then the mass would be twice that, and so on. There's also a concept known as average density. Okay, so you can think of average density as kind of the density of an object made up of heterogeneous materials averaged out over its whole volume. And by heterogeneous materials, what I mean is something that's made up of several different things. Okay. So for example, a boat. A boat floats because its average density, and that includes air spaces, is less than the density of water. If you think about the boat itself, whether it's a large steel ship or just say a fiberglass smaller boat or an aluminum canoe, whatever, the material that the boat itself is made out of is more dense than water and should by all rights sink. But when you take the average density over the entire volume of that boat, you end up with something that's quite a bit less than the density of water. And that's largely because of all the air spaces within it. the air has a density that's very low compared to the density of water. And so you average in all those air pockets and you get something that's less dense, and therefore it'll float on top. If the boat springs a leak and starts filling up with water, then you're essentially replacing air in those airspaces with water, which when averaged together with all of those materials like aluminum or steel or fiberglass that are more dense than water, your average density now is going to be greater than water and the boat's going to sink. There's also the fact that humans float also in water, and that's because even though, when we think of things like muscle and bone and skin, all of that is more dense than water, and so we might wonder, why don't we sink? And we might think, oh, well, with airspaces, we got air in our lungs. Well, yeah, but not very much, although that does help. Actually, what it is fat. Humans all contain a certain amount of fat, no matter how skinny you might be, and that fat is quite a bit less dense than water. And so when you average out the density over the entire volume of your body, most people come out to be a little bit less dense than water. And that's why humans are able to float. On the other hand, it's a curious fact that actually apes are very poor swimmers. And that's because they're all muscle. They've got very little fat in their bodies. And so their average density has come out to be greater than the density of water. And so when they go in the water, they just sink like a stone. And in fact, that a lot of zoos have on their exhibits involving apes and chimpanzees and things like that. In some of them anyway, basically all they have between the spectators and the apes is like a moat of water, because they know that the apes cannot get across that moat of water. They'll just sink like a stone if they go in the water. So yeah, that's all down to average density. The relationship between density in gases and liquids is that objects of lower density will rise above objects of greater density in both gases and liquids, as long as they don't, like dissolve or react with each other. And, well, an example of that actually would be boats floating on water. The average density of the boat is less than the density of the water, so the boat rises to the top. Or, humans floating in water, as I was saying, because of the fat in our tissues, humans are less dense overall than water is, so we float. Also, oil on water. Oil and water don't mix with each other because they're two different kinds of molecules. We'll get into more detail on this later when we get to the chemistry section, but basically water molecules are polar and oil molecules are nonpolar, which for our purposes just means they repel each other. They don't mix, they don't react with each other, and the oil has less density than the water, so the oil rises to the top. On the other hand, if you take something like alcohol, which also has a lower density than water, it will not rise to the top when you mix it with water. In fact, it mixes in, because water and alcohol are both polar type molecules, and so they will mix together rather than separating. So that's why I sort of put that exception in. If they mix together like alcohol and water do, then you won't get two separate layers. Another example would be a helium balloon. The helium in the balloon is less dense than the air around it, and so it will tend to rise up into the atmosphere until it gets to a point where the air is so thin that the density of the air is about equal to the density of the helium in the balloon. And that's quite far up if you ever let go of a balloon. There are some factors that affect density that you might have to be aware of depending on what type of material you're measuring the density of and how extreme these conditions get. Temperature is one factor that affects density, and that's because as temperature increases, volume will increase. And if volume increases, density decreases. Because volume is on the bottom of the fraction, so if you divide by a bigger number, the result is smaller. So density decreases as temperature increases. This is especially true for gases. Changes in temperature make a huge difference in the densities of gases. And it's true to some extent for liquids, not as much as it is for gases. And it's true to a small extent for solids. The volume of solids can increase noticeably with an increase in temperature, but not as much as it does for liquids. And liquids don't increase as much as gases do. So it's really a big factor for gases. And another factor would be air pressure. If the pressure increases, volume will decrease. And if volume decreases, that means density increases. So if pressure increases, density increases. And again, this is especially true for gases. Even a small change in the air pressure can result in a big change in the density of a gas. Also true to some extent for liquids, but not as much as gases. And for solids, air pressure really doesn't make that much difference at all. That's because the particles in a gas, as I said a moment ago, are far apart from each other, and even a small increase in pressure can result in those particles being pushed closer together. And that would be a decrease in volume. Notice how neither of these factors affects mass. And that's because mass is just a measurement of the amount of matter in an object or a sample, and environmental factors don't really affect that. Really, the only way to affect the amount of mass in the sample is to change the sample itself, like by chopping it up or something like that. So temperature and pressure will both affect volume. Okay. Okay, that's about a half hour, so I'm going to stop for the second